Alright guys, hope everybody's doing okay. What we're going to do right now is take a look at something called a macromolecular solid or covalent network solid. Okay, this is one of the last, types of substances we need to look at in this unit, and it's a relatively short lesson here. There are some extra videos and extensions you could look at. I might link them in various places on my YouTube channel or on Edpuzzle if you're interested in those. But let's take a look at what I mean by a macromolecular or covalent network solid. The prefix macro obviously means big, okay? So I have a picture of one of these macromolecular solids here. So it's a large network, okay, there's that macro prefix again, large network of covalent bonds, okay, hence covalent network, all right? It's where you literally just have atom after atom after atom after atom ongoing here, connected through actual chemical bonds. Okay, note that it says all chemical bonds are solid lines. You have all solid lines here. So normally what we have is you have, I don't know, a water molecule. Okay, so here's your water molecule. And that's it, right? That water molecule has two chemical bonds, and it's attracted to another water molecule, through this intermolecular force of attraction, right? So this is our hydrogen bond right there. Remember, hydrogen bond isn't isn't an actual bond; it's a force of attraction. Okay. And we talked about that earlier. So here, though, for a covalent network, we don't have any intermolecular forces. Everything is intra, okay? Intramolecular in terms of the bond, okay, from one atom to another one. Huge network of covalent bonds, as I just scribble everywhere, okay? So let's take a look at this in a little bit more detail here. This is what I was just trying to draw on the previous slide. Okay, so what do I want to do here? Whatever. So you can see that this is our water molecule here, and we just have all of these intermolecular forces attracting one water molecule to the next. Whereas we have our covalent network where we have covalent bond after covalent bond after covalent bond, okay? Students, for some reason, have a hard time understanding the difference here. What's the difference between covalent and a covalent network, or network covalent? The difference is the molecular or covalent solid is a solid where you have individual covalent molecules attracted to each other pretty strongly, since it's in the solid form, through intermolecular forces like London dispersion, dipole-dipole, and hydrogen bonding. What we have for the covalent network, okay, is all of these atoms being connected through chemical bonds, okay? There's not really an intermolecular force here at all, okay? It's a huge, huge structure where it's bond after bond after bond compared to intermolecular forces attracting them, okay? So I know I'm repeating myself a lot, but students are having issues with this. They've had issues with it in the past. I want to make sure you know the difference between those two. So there's only two that you're really required to memorize or know for the covalent network. They're on the next slide, I guess. Sorry. So let's go through some properties first. Large network of interconnected covalent bonds, talked about that. No individual molecules, talked about that. Very important. Okay. That makes this extremely strong. Okay. A covalent bond is definitely stronger than an intermolecular force. Okay. So that intramolecular covalent bond is definitely stronger, is definitely harder to break than an intermolecular force like a dipole-dipole or even hydrogen bond attraction would be. Other properties we need to know. Once you remember the examples of covalent network, these will be easier, okay? So some properties, you have very high melting point because you must overcome the strong covalent bond to melt. So in order to break up that rigid structure, that solid structure you have, you need to loosen and overcome some of that bonding. It's really hard to do because covalent network solids have this huge amount of covalent bonds, connecting all those atoms together. This is key. Electrons are localized. So I know we talked about localized versus delocalized in Unit 1. Localized means generally in the same location. So if you have a single bond, you're going to have electrons that are between those two atoms. So if you just pick one of the bonds up here, like this bond right here where the mouse is, those two electrons are localized in this region, okay? It's not like they're delocalized and can bounce to other atoms, okay? It's not like that in covalent network solids, which leads to this property here of them not conducting heat or electricity very well, okay? Since those electrons are pretty stagnant, there's not an easy way to have electrons flow, which is what conducting electricity is, okay? So if you recognize that, conducting electricity is that movement of electrons. We talked about it earlier where we have metallic bonding. Metallic bonding in metals is with that sea of electrons. There's that movement. Here because they're delocalized, here you don't have that, okay? So you don't have the delocalized electrons, therefore you don't have a good conductor of electricity. And they're very brittle because of the structure and the way they are formed, okay? So they're not very malleable at all. And when you look at some of these examples, you're like, well, they're not really metals, right? So metals have that good malleability and ductility, whereas covalent network solids will not have that. So the two you have to know, diamond or graphite, which is just carbon, okay? And quartz, which is SiO2, silicon dioxide. So you need to know what those two are. So if I mention diamond, graphite, or quartz, or silicon dioxide, if I give you the actual formula, you know that those are covalent network solids. There's a difference between diamond and graphite. Diamond is where you have your carbon with four other carbons connected to it, and you have a different geometry. Graphite is where you actually have them in the planar geometry, and you end up with sheets, like very thin sheets of carbon. That's why your pencil, which is not lead, which is graphite, which is carbon, when you write, it's just really smooth. You have these sheets of carbon just sliding off onto your paper. It's really cool. It's also a good lubricant because if you ever scribbled a bunch of pencil writing on your paper, you rub your hand over it, it's smoother than the paper actually is because you have all these really thin sheets of this trigonal planar geometry on your paper. Okay, so that's kind of neat. Okay, so I just went over this. Diamonds are an example of a covalent network where you have four carbons covalently bonded to each other. They tend to be hard and have a high melting point. You know that if you know properties of diamond. Graphite, though, is different. I have these highlighted here so you can see that the diamond was on the left. The way that is structured, that's the slide I had, or the picture I had on the first slide of the presentation. And here's graphite. You have layer after layer attracted through intermolecular forces, which you could easily break as you write. This video here, I'm not gonna show it right now. It's from Crash Course Chemistry. It's really, really good. It's on diamond and graphite, I believe, and it goes through some of this. I'll link it in Edpuzzle, or I'll link it on my YouTube channel if you want to watch it separately. It's about 9 minutes, so it's pretty cool. So graphite, like I said, has 3 covalent bonds in trigonal planar geometry, which forms flat sheets, and the sheets themselves are very strong. Okay, the sheets they're highlighted here, but one sheet is attracted to another relatively loosely by dispersion forces. So this tends to be a softer material and have a lower melting point. All right, so here's the last one, covalent network, silicon dioxide, SiO2, bonds in a 3D tetrahedral network similar to a diamond, which would give it, some structures similar to that of diamond. Okay, that takes care of covalent network. So that's a quick 10-minute lesson on that. Now that we're done with all the types of solids here, or really the type of structures, I guess, on average, you need to know this, on average, from strongest to weakest, I have on the slide here, so you feel free to copy it down. Covalent network is the strongest on average because it's all intramolecular forces, which are going to be very strong. Okay, so generally your highest melting point is going to be covalent network. The next strongest is ionic, so you have your Coulombic attraction there, electrostatic attraction. That's important to know. And then metallic. Okay, so covalent network, ionic, metallic, top three. After that, it's just covalent substances, like water, like carbon dioxide. So when you look at your intermolecular forces with the covalence, so you might want to add that in there. Remember, hydrogen bonding is generally the strongest. Dipole-dipole is a little bit weaker. And dispersion forces are generally the weakest. I say generally because you'll see so many examples. They feel like the College Board always comes up with the exceptions here for something with dispersion forces having a higher melting point than something with dipole-dipole or hydrogen because it might be a really big structure. So this is a general list, okay? But if there's data to prove otherwise, it's just there are some exceptions to these rules, okay? So have the general list in your head, but don't think of it as being cut and dry, black and white, because it's not going to be that way. So as a reminder here, if two substances are held together by dispersion, the more massive substance is stronger, so that has to do with the number of electrons that it would have. The greater the mass, the greater electrons it will have, which means it is more polarizable. I mean, I think I made it perfectly clear here that if you're talking about dispersion forces, polarizability has to be mentioned, okay? We'll do plenty of practice with that. But polarizability is the ability to make a temporary dipole, okay? The more electrons you have, the greater ability to make that temporary dipole, and therefore have that temporary attraction, which holds the substances together, okay? More surface area, flatter, straighter is better, that is stronger as well. So generally you go by mass first and then by surface area. Remember, all molecules have dispersion forces, so even if you have water has hydrogen bonding, dipole-dipole, Lennon dispersion, okay? So all molecules have dispersion, but they're insignificant if it has hydrogen bonding or dipole-dipole in addition to that. Okay, so if both dipole-dipole or hydrogen bonding, look at electronegativity to determine the strength of your dipole. So if both molecules have similar dipoles, the one with more dipoles will be have a higher force of attraction. Okay, so if you have two structures that are polar, look at the electronegativity difference and see which one is more polar. The one that's more polar is going to have a stronger intermolecular force. Okay, so the example that we may have done before is HF compared to HCl. Okay, HF and HCl are definitely both polar, but HF has a bigger dipole, so it's a stronger force of attraction than HCl. So this would have a higher force of attraction, higher melting point, boiling point, whatever. Okay, because of that. So that's how you want to think of those. Quick chart to summarize this. If you want to copy it in your notes, you can. It might even be in there already, I'm not sure. But it gives you a nice little summary of the type of solid, what makes up that solid, the forces between particles, properties, which you need to know, and a couple examples. Okay, so take a look at that. Write down that if you need to. And that kind of takes care of our different types of solids. Next, we're going to look into some properties that they may have, like a little more in depth in terms of the properties, looking at something like surface tension, cohesion, adhesion, melting point, boiling point, a few other ones. Okay, we'll take a look at some of those where we tie in what we know here and apply it to some of those properties that we might see in everyday life. Okay, that takes care of today, guys. A relatively quick lesson. Hope it made sense. If you need any help, just let me know. All right, thanks.